Hello everyone. Today we'll talk about this topic, that is basics of cardiac cycle, heart sound and murmur. Okay. First of all, let us discuss what is cardiac cycle. Cardiac cycle is the event that occurs in 0.08 to 1 second, in which there are two phases, that is systole and diastole. Whenever we are talking about systole, we talk about ventricular systole. Whenever it is written diastole, it is ventricular diastole. Clear? Now, systole, that is ventricular systole, has three components. So, suppose this is RA, LA, RV, and LV. Okay. Now, we are talking about ventricular systole, that is ventricular contraction. So, initially, at this stage, LA, RA, RV, LV are in relaxed state. That is, all of them are in diastolic stage. Okay. Now, the first phase of ventricular contraction is isovolumetric contraction. Okay. So basically, what happens is when the systole starts, this AV walls are closed and this semilunar walls are also. So here ventricles are isovolumetric. That is, there is no input to the ventricles as well as no output to the ventricles. Okay? So it is just like a closed chamber. Okay? And when it starts contracting, since all the four walls are closed, the volume would remain same. Okay? So the first phase would be isovolumetric contraction. Since isovolumetric contraction keeps the volume same, but it will increase the pressure in ventricles. And when the pressure in ventricles increases further, there is opening of these semilunar walls. Yes. When this pressure is more than the pressure in aorta, these semilunar walls opens up. Okay. And then ejection phases start. That is, there is ejection of blood from RV and LV to aorta and pulmonary artery. Okay. This ejection phase is divided into first part, that is rapid ejection phase, and second part, that is slow ejection. Okay. Now, what is end systolic volume? So after systole, this volume is left in the ventricles in one cardiac cycle, and this is 50 ml. Okay. While end diastolic volume is the volume that is present in the ventricles before the systole, and this is also known as preload. Okay. And we are talking about each ventricle, that is end systolic volume in each ventricle is 50 ml and end diastolic volume in each ventricle is 130 ml. So basically the ejection fraction is 65%. Ejection fraction is end diastolic volume minus end systolic volume upon end diastolic volume. Okay. So how much of the volume is ejected upon how much initial volume was there? So it comes out to be 130 minus 50 by 130, 80 by 130, approximately equals to 65%. Clear? Now this is how we draw. So this S1 and this S2 again and again S1. So we know that S1 is because of the closure of mitral and tricuspid valve, while S2 is because of the closure of aortic and pulmonary valve. So between S1 and S2, that is when tricuspid and mitral valve closes, and till the time when aortic and pulmonary valve closes, we have this phase that is systole. And second phase is diastole, that is till the time when mitral and pulmonary valve close. Okay. Now S1 is due to closure of mitral and tricuspid valve. This first phase is isovolumetric contraction. That is the phase when ventricles are contracting but all the four walls are closed, so volume remains same. Then at this point, there is opening of aortic and pulmonary valve, leading to first phase of rapid ejection and the second phase of slow ejection. And at S2, there is closing of this aortic and pulmonary wall. Okay? So at this point there is opening of aortic and pulmonary wall, and at this point there is closing of aortic, and at this point there is closing of mitral and tricuspid. Okay? Now diastole. Again we will just divide the diastole into phases. First is protodiastole, which is a component of isovolumetric relaxation only. So what happens in isovolumetric relaxation is that we know that at this phase there is closing of aortic and pulmonary valve, and tricuspid and mitral valve are already closed. So again ventricles are closed chamber, so definitely the volume would remain same and they would start relaxing. So the pressure in ventricles start dropping here. This phase is isovolumetric relaxation. Then when the pressure in ventricles falls below the pressure in atria here, there is opening of mitral and tricuspid valve, leading to first phase of passive filling, which is almost 70% part of the filling, and another phase of active filling, which is because of the atrial contraction or atrial systole. So again, here we can see we divide the diastole phase into three parts. First one is isovolumetric relaxation. Here all the four walls are closed. At this point, when the pressure in ventricles is less than the pressure in atria, there is opening of tricuspid and mitral valve, leading to this phase of passive filling. And at this last stage, there is atrial contraction, leading to active filling. Yeah. So we should definitely understand this diagram. After this only we can understand how the murmurs are there, how we define the murmurs, or what is the shape of them. So suppose if murmur is there in whole of this part of systole, then it is pansystolic. If it is in mid part, only mid systolic. If it is in mid and late part, ejection systolic. Again in diastole, if it is in mid part, mid diastolic. Okay. This is how, or in first part early diastole. This is how we define the murmur. Now systole and diastole has duration of, systole is having duration of 0.27 seconds. Diastole is having duration of 0.53 seconds. Definitely diastole is somewhat long. Diastole is a good phase because it helps in filling of ventricles, and more the filling we know, more is the contraction, according to Frank Starling. Another good thing is that blood supply in coronary arteries is mainly in diastolic phase. Now, right atrial pressure changes in jugular pulse. So, definitely we should know how jugular waveform is formed. This is suppose right atrium in which SVC is draining. Okay? And SVC is formed by subclavian and jugular. So, since jugular vein is in direct continuation of RA, the jugular pulse pressure changes are actually RA pressure change. Now, how the pressure change in RA? So, suppose this is atrial contraction phase. So, this produces positive pressure in RA, and this wave is known as A wave. So, first of all, we are here starting from here. So, here, last phase. We know that this phase is a phase of atrial contraction. So, we are starting from here. First of all, there is this A wave due to atrial contraction. Then we know that there is S1. It is closure of mitral and tricuspid valve. According to this diagram, also we can see that after this phase, there is S1. Here. So there is closure of mitral and tricuspid valve, which will generate a small pressure wave in RA. Okay, and this is known as C wave. C wave is because of the closure of our tricuspid and mitral valve. And we have this X descent. Okay. Again, the pressure started rising in the atria because of the filling of the blood from the vena cava. Okay, so this V wave is because of the filling of the atria. Okay. Then we have this Y descent, and this is due to the passive filling. So when there is passive filling of the ventricles, the blood flows from the RA to RB, leading to decrease in the pressure of RA. So we have this A wave, C wave, X wave, B wave, and Y wave. A is because of atrial contraction. C is because of closing of valves. X descent is descent because of decrease in pressure in RA. B wave is because of increase in pressure in RA due to filling of RA. And Y descent is because of passive filling of RA. Okay. Now we have various changes in JVP in different diseases. So suppose a patient is having, let us first discuss this. A wave is because of atrial contraction, C wave bulging of tricuspid valve into RA due to isovolumetric contraction. Then we have V wave, venous return before tricuspid valve open, and Y wave after opening of tricuspid. To discuss. Now suppose in some condition like uh, junctional rhythm or AV block, like junctional rhythm and ventricular tachycardia. In these two conditions, sometimes what happens that atria and ventricles contract at the same time. Okay. Now we have already discussed that A wave is because of atrial contraction, and when ventricle would contract at the same time as ventricles, as atria, so there would be a very big A wave, which is known as cannon A wave. So another thing in JVP is there was a patient is having cardiac tamponade. So there is defective filling of ventricles. So this Y wave we know is because of passive ventricular filling, and it got disrupted in case of cardiac tamponade. So Y descent would be absent. So we have JVP like this: A, C, X, E. Y descent is absent in cardiac tamponade. Here's some other pathologies in JVP that we'll discuss later. Now heart sounds. So some of the important normal heart sound are S1, which is because of closure of mitral and tricuspid valve. Duration is 0.15 seconds and frequency is 25 to 45 hertz. It is a high pitch sound. So we can listen to S1 with the help of diaphragm. S2 is because of the closure of aortic and pulmonary valve. Duration is 0.12 seconds and frequency is 50 hertz. Again, it is high pitch and we can listen to it with diaphragm. S3 is something which coincides with the period of rapid ventricular filling. So the rapid ventricular filling phase is the passive filling phase, and it can be heard in many normal young individuals or athletes. So what is S3 basically? That this is S1, S2, S2. This is systole, this is diastole. In diastole, we have first part that is isovolumetric relaxation, then rapid passive filling, then active filling. So during rapid ventricular filling, there can be S3, which can be normally heard in normal young individuals or pathologically heard in heart failure with reduced ejection fraction. So basically S3 would be somewhere in this phase. S3 would be here. Then now S4 can be heard immediately before S1, that is in this phase. It is in phase of atrial contraction. When ventricle is stiff in conditions such as ventricular hypertrophy, it can normally be heard in normally old individuals or adults. Yeah? And it can be pathologically heard in heart failure with preserved ejection fraction, atrial aortic stenosis, and HOCM, hypertrophic cardiac. We can also have S4 in LVH. Yeah. So from this diagram, we will know that this is S1, S2. S3 is somewhere in here in passive filling phase, and we have S4 here just before S4. So it is quite clear here that both S3 and S4 are diastolic sounds. Both are low pitch sounds. That is, both are heard with well of syringe. Yes. Now, what are the causes of loud S2? Tachycardia can lead to loud S1, or short PR interval, which ultimately leads to tachycardia, leads to loud S1. Then we have early phase of rheumatic mitral stenosis until calcification. So when the calcification occurs in mitral stenosis, S1 would become soft. Till then, S1 is loud. Now, in patient with hyperkinetic circulatory state like thyroid toxicosis, pheochromocytoma, pregnancy, severe anemia, these cases would be having loud S1. Causes of soft S1: bradycardia, long PR interval, late mitral stenosis when walls are calcified, and after exposure to beta blockers. So beta blocker ultimately leads to bradycardia, which would lead to soft S1 and mitral regurgitation as well. And S2. S2 is a very important sound. So S2 has two components. A2 is because of closure of aortic valve, and P2 is because of closure of pulmonary valve. So this is a normal S2. Okay. Now, whenever there is inspiration, patient inspires, blood in right side of the heart increases, while in left side it decreases. So there would be delayed in the closure of pulmonary valve there, leading to increase in this gap. So A2, and during expiration, blood in left side of the heart increases while right side decreases, leading to narrowing of this gap. So normal splitting of A2 P2 can only be appreciated in inspiration, because in expiration they come too closer that we are unable to appreciate them. Okay? Now, where to listen for splitting? Okay. So basically, P2 is a very soft sound as compared to A2, because it's because of the pressure closure of pulmonary valve, which is a low pressure valve as compared to aortic. Okay. So P2 is soft and is heard only in pulmonary area. Okay. So we are able to listen P2 only in pulmonary area. So splitting can only be appreciated in pulmonary area. Okay. Now, if splitting is appreciated in other areas too, that means we are able to listen to P2 in other areas too. And this suggests that P2 is loud. Okay. And the causes of loud P2 are anything that can lead to pulmonary hypertension and lead to loud P2. Now here is this question. It is S3 is heard in which phase of cardiac cycle? So we have already discussed that it is a diastolic sound. Now what is the opening snap? The opening snap is due to the opening of mitral and tricuspid wall, and it is heard only in mitral stenosis and tricuspid stenosis. Okay? So basically we have already discussed that whenever the wall closes, it produces sound. So S1 is because of closure of mitral and tricuspid wall, while S2 is because of closure of aortic and pulmonary wall. But in pathological conditions like MS and TS, we can also listen to the sounds that is opening of mitral and tricuspid wall, and these are known as opening snaps. So in this diagram, we can know that at this point, mitral and tricuspid wall open. So this is the point where opening snap is. And at this point, there is opening of aortic and pulmonary wall. So ejection click is present here. Okay. So ejection click is a systolic sound again, and opening snap is a diastolic sound. So ejection click is due to opening of aortic and pulmonary wall in patients of aortic stenosis and pulmonary stenosis. Okay. So again, this diagram we have ejection click here, opening snap here. Now again, here is this question that opening snap is due to. So it is because of opening of mitral and tricuspid. The question is S1 is due to. So it is closure of mitral. Closure of aortic and pulmonary wall produces S2, while opening of aortic and pulmonary wall produces ejection. MURMURS. So Murmurs are, let us first discuss about S2 again. That is splitting of S2. Because S2 splitting is something very important. The normal S2 splitting we have already discussed. Now, what are the pathological S2 splits? So, in pathological S2 splits, uh, let's discuss it here. We have discussed that normal S2 split is A2P2, and in expiration becomes a single sound. Okay. Now, there is a condition in which there is fixed and wide splitting of S2. That is, we can appreciate splitting in inspiration and expiration, and the gap is same in both. So, the condition which can lead to fixed and wide splitting is ASD. That is atrial septal defect. Then we can have fixed and variable splitting. Sorry, wide and variable splitting, in which splitting can be appreciable both in inspiration and expiration, but there would be more splitting in inspiration and less splitting in expiration. So we have the condition known as VSD, in which there is fixed and wide splitting. Then there is also a condition in which there is a reverse split. That is A2P2. This is a normal phenomenon. A2 comes first and P2 second. And during expiration it decreases. Okay. But suppose if P2 comes early and A2 comes late. Okay. So what will happen that during expiration, we know that definitely pulmonary sound would come early, and during expiration, P2 would become close and A2 would become later. Okay. So just give me a minute. So this is normal splitting. Okay. Now, in what happens in reverse splitting is P2 comes early and A2 comes late. And we have, as we have already discussed, that during expiration, A2 would become late and P2 would become early. So P2 would become early and A2 would become late. So in reverse splitting, there would be splitting and it would be appreciated in inspiration and expiration both. First sound in P2, second is A2, and one other important thing is that it would be more in expiration. Okay. As we have already discussed in wide and variable splitting, splitting would be appreciated in both phase, inspiration and expiration, but it would be more appreciated in inspiration. But in reverse splitting, splitting would be there in both inspiration and expiration, but splitting would be more wide in expiration. Clear? The condition which would lead to reverse splitting is anything that would delay A2, like left bundle branch block. Okay, severe aortic stenosis. Okay. Now murmurs. So basically, murmurs are something that are produced due to turbulence of blood flow. Normally, blood flow in heart is laminar. So there is no turbulence, no murmurs, no heart sound, no added sounds. Normally, the heart sounds that are produced is due to closure of valves. There is no added sound due to the flow of blood because the blood flow is laminar. But when there is turbulence of blood flow, then there would be a murmur. Normal blood flow is laminar and silent up to a critical velocity. Above this critical value, blood flow becomes turbulent and produces sound known as murmurs. Now, murmur can be in systolic phase or diastolic phase. So, murmur can be systolic murmur or diastolic murmur. And we have already discussed that systolic murmur can be mid-systolic, late systolic, pan-systolic, and diastolic murmur again can be mid-diastolic, early diastolic. Systolic murmurs can be functional, like in anemia, pregnancy, or also can have some organic causes like MRVSD, while diastolic murmurs are almost always organic, like in mitral stenosis and aortic regurgitation. Now murmurs in various conditions. Let us first discuss the grading of murmur. Grading of systolic murmur: 1, 2, 3, 4, 5, 6. If the sixth grading of systolic murmur, one is that murmur is heard with difficulty. Okay. Second is murmur is heard moderate in intensity and without difficulty. Clear? Third is murmur is loud. Clear? But till grade 3, we don't have any thrill. Grade 4 is murmur is loud and with thrill. Okay. Fifth is murmur is so loud that if we lift one part of the stethoscope, then also we can able to listen to the murmur. So only one part of stethoscope is able to listen to the murmur. While grade 6 says that murmur is so loud that we can listen to the murmur with stethoscope 1 inch above the chest. Okay? And in grade 5 and 6 also thrill is present. Okay? So thrill is present above grade 4 murmur. As we have already discussed that systolic murmurs can be functional. But if murmur is above grade 4 or above grade 4, that is thrill is present in systolic murmur, then it is almost always organic. Yes. Now diastolic murmur. So in diastolic murmur, we have only 4 grading. Okay. As we have already discussed, that if diastolic murmur is present, then it is almost always organic. So we have less grades for diastolic murmur. So the grading of diastolic murmur is grade 1, grade 2, grade 3, and grade 4. Now let us discuss about grading of diastolic murmur. Diastolic murmur, grade 1, then we have grade 2, we have grade 3, we have grade 1, it is barely audible, audible but soft, easily audible, and loud. Again, in grade 4, diastolic murmur, releasable. Now, murmur in various important conditions. The first is mitral stenosis. Mitral stenosis means that there is difficulty in opening of the mitral wall. Clear? So, suppose this is a time for opening a mitral wall. When this wall should open like this, it is opening like this. It is, it has, it is not completely open. This would lead to turbulence of blood flow through this wall, and we will having a murmur. The murmur would be produced due to mitral stenosis whenever there is opening of mitral wall. But when mitral wall closed, there is no defect in closing of mitral wall, so there would be no murmur. Now we should know that at which point the mitral wall opens. Okay. So we know that this is a diastolic phase. S1 is because of closing of mitral and tricuspid wall. S2 is because of closing of aortic and pulmonary wall. This phase is isovolumetric relaxation phase. Then at this point, we have opening of mitral and tricuspid wall. Then this is passive filling phase and this is active phase. Clear? So at this point, we have opening of mitral wall. Clear? Now, when mitral wall opens at this point, and since the patient is a mitral stenosis, we have a sound because of opening of mitral wall, which is known as opening snap. Opening snap is a high pitch sound. That is, we can listen to it with the help of diaphragm. Now, when the mitral wall opens, the murmur starts from this point. Okay. When the murmur starts from this point, this is how murmur goes. When at this point there is atrial contraction, so the blood would come from LA to LV with high pressure. Okay. And then, since the blood is coming at high pressure, the murmur intensity increases. Okay, the murmur would increase in late phase. So this is basically a mid-diastolic murmur because in early diastolic phase there is no murmur. Murmur is there in mid-diastolic phase with there is increase in the intensity of murmur in late diastole or pre-systole, we can say. So this is pre-systolic accentuation. Yeah. So we can define the murmur of mitral stenosis as mid-diastolic murmur with pre-systolic accentuation with opening snap. And murmur of mitral stenosis is a low pitch murmur. That is, we can listen to MDM with the help of bell of stethoscope. Clear? So mitral stenosis murmur is mid-diastolic rumbling murmur with opening snap with pre-systolic accentuation. Okay? Now suppose if the patient of mitral stenosis is in atrial fibrillation, which is quite common, then this pre-systolic accentuation would disappear because there is no effective contraction of the ventricles. So there would definitely no increase in the intensity of murmur. So in that case, the murmur would be mid-diastolic murmur without pre-systolic accentuation. Clear? Again, if the patient is having non-calcified valve here, so we would also have loud S1. Clear? Now, second condition is mitral regurgitation. So, regurgitation means that there is difficulty in closing of the valve. Okay. Now, mitral valve is unable to close. Now, mitral valve closes during systolic phase. We know that. Okay. Now, suppose this mitral valve closes, but it is unable to close properly. That is when it should be like this. It is like this. Okay. So, there is an opening here. So, we know that S1 is because of the closure of mitral valve. Now, whenever the mitral valve closes, the blood will leak from LV to LA and this produces turbulence and murmur. So mitral valve will close at this point. Okay. This is the phase of isovolumetric contraction. But when the ventricles would contract and there is a phase of isovolumetric contraction, mitral valve is not completely open. So there is leakage of blood from LV to LA through this uh, defective mitral valve. So there would be a murmur in this phase. Now this is a phase of rapid ejection, that is opening of aortic and pulmonary valve here would lead to ejection of the blood from LV and RV. Now at this point also mitral valve is not completely closed. So blood will leak from LV to LA again. So murmur would be in this phase too. And this is a phase of late ejection. But again, mitral valves are open here. So definitely murmur would be in this area too. So this is pansystolic murmur of mitral regurgitation. Yeah. Now again VSD. VSD is something that there is a defect between RV and LV. Now during diastole, the pressure in LV is 0 and pressure in RV is 0. So since there is no pressure gradient, there would not flow blood from LV to RV or RV to LV. But when during systole, LV start contracting or RV start contracting, but pressure in LV is more than RV. So systolic pressure in LV is 120, while in RV it's 25. Okay. So there is flow of blood from LV to RV, and it would occur in whole of the systole. So we have murmur in whole of the systole, and it is again a pansystolic murmur. Clear? Now in aortic stenosis, what happens in aortic stenosis is that there is defect in the opening of the aortic valve. Now aortic valve opens at this point. And since this patient is of aortic stenosis, the opening of the aortic valve would produce a sound known as ejection click. Then now when aortic valve opens at this point, but it is unable to open properly, that is when it should open like this, it is opening like this. It is narrowing in the opening of the aortic wall, so it would produce turbulence. The murmur would start from here, increase in the rapid phase, and it would become inaudible in slow ejection phase. So it would be ejection systolic murmur, or we can also call it as mid systolic murmur. Characteristic of murmur of AS is that it rises first in rapid ejection and then decreases in slow ejection. So it is a crescendo, decrescendo murmur, or we can also call it as diamond shaped murmur. Clear? And it is associated with ejection click. And whenever there is severe AS, we've already discussed, then there can be this reverse splitting of S to 2. Now, aortic regurgitation. So, aortic regurgitation means there is defect in closing of aortic wall. Now, aortic wall closes at this point, S2. Since there is defect in closing of aortic wall, so this phase, that is isovolumetric relaxation phase, aortic wall would be open, or we can say that it is not properly closed. So there is leakage of blood from aorta to the LV. So we have a murmur here. Now since LV is a small cavity and aorta contains a lot of blood, so the flow would keep on decreasing. And during this phase, that is passive filling phase, since LV is also receiving blood from LA, okay, so there is decrease in the leakage of blood from aorta to LV. So the murmur would keep on decreasing. So we can say that the murmur in AR is diastolic, and it is mostly early diastolic, and it is a decrescendo murmur, that it decreases with time. Okay. AR is very important for our questions because we have a lot of signs in AR, like increase in pulse pressure. Why? Because systolic pressure increases in AR because there is a lot of blood in LV cavity. Okay. While diastolic pressure decreases because during diastole there is backflow of the blood from aorta to LV. Okay. We can have this water hammer pulse, that is bounding pulse. So we have systolic good pulsation, while in diastolic phase the pulse would run away. We can have various signs like Muller sign, in which there is dancing uvula. We can have Dean-Lucet sign, in which there is nodding of head. Then we have pistol shot, femorals, dancing carotids. A very important sign known as Hill sign, in which difference between BP of upper limb and lower limb. It is lower limb BP would be more and upper would be less, more than 20. And it is very important sign. The most important sign is Hill sign, and it is used to grade the AR. That is, if difference is more than 20 was less than 40, it is mild. If it is more than 40, less than 60, it is moderate. If it is more than 60, it is severe. Yes. Now, areas of auscultation. First area is mitral area. It is in left fifth intercostal space in mid-clavicular line. Okay. Tricuspid area, it is right parasternal border in fourth intercostal space. Aortic area is right parasternal border in second intercostal space. Pulmonary area is left parasternal border in second intercostal space. And Aux point, it is left parasternal border in third intercostal space. So Aux point is the point where we listen to the murmur of aortic regurgitation. Thank you very much, guys.